Hello and welcome back to Miss White's Mhf4u math class. We're doing the Chapter 8 review today. So basically what I would like you to do is, as we're going along, I'd like you to pause and do the questions. So don't just follow along and, copy the answers. I would like you to try them first and then see how you do. I will take them up as we go. We're going to talk about each chapter and like each section in the chapter and then do the questions. And hopefully this will help you to review for the test. So the first thing we're going to do is 8.1. 8.1 was pretty straightforward. It's just an introduction to logs and exponentials. So the exponential function is the inverse of the logarithmic function. Oops, can't spell. Logarithmic function. So these are inverse of each other. And in 8.1 we learned how to, sorry about the zooming, we learned how to switch from exponential form to logarithmic form and vice versa. We also learned about the graphs, what the graphs look like. So if you think about y equals a to the x, right, that is going to look like this right here, where we've got a horizontal asymptote at y equals 0 and a y-intercept at 1, and this is if a is greater than 1, okay? If you have a between 0 and 1, so 0 less than a less than 1, then we're still going to have that horizontal asymptote y equals 0, but it's going to be a horizontal flip like that. We still get a y-intercept at 1. All right, so the inverse, the log, y equals log base a of x. If a is greater than 1, then it looks like this. So instead of having a horizontal asymptote, you get a vertical asymptote, and instead of a y-intercept, you get an x-intercept. And the same goes for a between 0 and 1, but you get a vertical flip, okay? Because these are reciprocals of each other, so you have to switch the x and the y. All right, the domain for exponential is x in r, range is y in r, y greater than 0. So when we do the inverse for the logarithm, it's going to be the reverse, right? So the x's become y's and the y's become x's. So the domain here is x in r such that x is greater than 0, and the range is y in r. Okay, so hopefully you can see how those match up there. So this domain matches this range, and this range matches this domain. Just like that. Okay. So we're going to switch between exponential and a logarithmic form. Write in exponential form log base m plus 10 of 6a equals 7w minus 2. So this is going to be my base in the new answer. So m plus 10 is my base, put in brackets. And these guys are essentially switching places. So the argument becomes the answer, and this answer is going to become the exponent, like that. Okay, so now we're going to do example B. You could pause and do example B on your own first. Write in logarithmic form. You just have to, again, switch these with that same base. So log base s of, and then r is going to be in our argument, and k over 3p is going to be our answer. Okay, so that's basically all you get from 8.1. 8.2 is graphing. This graphing is not that different from chapter 1. The only thing is that you're not given a parent function. You're not given all the points of the parent function. You're going to have to figure out those points. So we have a new parent function, y equals a log base m of k x minus d plus c. And those points will change depending on what your base is, right? So A is still your vertical flip, vertical stretch slash compression. K is still your horizontal flip, horizontal stretch or compression. D is moving left or right. C, is moving up or down. Okay, now it says write the equation of the graph after vertical flip, vertical stretch by 2, horizontal flip, horizontal stretch by 3, a move to the right by 4, and 1 up. This probably wouldn't be out of 3 marks. It would be out of more. So I didn't mean to leave the marks on there. So you can go ahead and pause it. I'm going to go ahead. So when you're done, unpause it and come back and double check your work. So we're using the parent function log base 2 of x. So we're going to use that base 2 in there. Vertical flip, vertical stretch by 2. That tells us a equals negative 2. Horizontal flip, horizontal stretch by 3. That's k. And because it's a horizontal stretch, it's the opposite of what you think. So negative 1/3. A move to the right by 4. So d is equal to 4. And up by 1. C is equal to 1. So y equals negative 2 log base 2 of negative 1/3 x minus 4 plus 1. Okay, you don't have to write your A, K, D, and C in there in order to get full marks. You could just write the equation, but you get the idea. Okay, make sure you're putting brackets here as well. So then now it asks us to sketch the parent function, transition graphs, and transformed function. So we're going to go ahead and do that. We have log base 2 of negative 1/3 x minus 4 plus 1. By the way, you do want to use a ruler, but my ruler doesn't really work with my tablet, so I'm not going to be using a ruler today, but you should definitely use a ruler. And of course, as with the other questions, I do want you to pause first and try the question on your own. I have a horizontal and a vertical flip, so I'm going to make this pretty symmetrical. I just wish it was a little bit more straight, but yeah, I don't have a ruler, so what are you going to do? 2, 3, 4, 10. 1, 2, 3, 4, 15. So as much as I have drawn, I will label. If you don't want to label so much, don't draw such a big grid. You do want to draw a pretty substantial grid though, because you don't want to it to be too small and then not have enough detail. I might have drawn too much on this y-axis here, but 2, 3, 4, 5. Hopefully I counted properly for all of those. So my parent function, log base 2 of x. So this is the inverse of 2 to the x. So we can just use those points from 2 to the x and reverse them. So if I use 0, 1, 2, 3, 4, right, then 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. That's about as far as I can get on my graph, so I'm going to leave it at that. So then I'll graph those. So this is actually 1, 0, 2, 1, 4, 2, 8, 3, 16, 4. So 1, 0, 2, 1, 4, 2, 8, 3. And if at any point I'm going too fast for you, you can pause it and, make sure that you get enough time to process. Pause it, go back, rewind, whatever. Up to you. You're controlling the pace, and you can also change the speed on YouTube, so you can make me play at half speed if you like. Okay, so that's my parent function. I've drawn in my asymptote as well, x equals 0. Don't forget to label it. And then I'm gonna start doing the other transformations. I'm gonna use different colors. You don't have to use any different colors, but I prefer it just for myself when I'm drawing so that I can see more clearly. But for you, if you only have a pencil, totally fine. Don't worry about it. I'll be able to read your work whether you have colors or not. It's just for myself. I like to have colors. Okay, so I'm going to do my vertical flip, vertical stretch first. So that's multiplying all the y values by -2. Again, just like we were doing in chapter 1. Nothing new. No new news. So this is a 2. I'm going to go to -4. This is a 3 going to -8. Is that 8? It's not 8. That's 7. 8. There we go. And then, wait. 3 times 2 is 6, not 8. Okay. Sorry, getting carried away. There we go. And then this is at 4, y equals 4, so I'm going to go to -8. Okay, and then I've still got my same vertical asymptote. Whoops. Try not to cross over, just trying to get through these dots in a curvy and attractive manner. I kind of missed, so I'm just going to make them a little bit bigger so that they fit. Okay, y equals -2 log base 2 of x. So I'm not expecting it to be totally perfect, but I do want you to try to hit those points as best you can. Okay, then we're going to do the horizontal stretch and flip. So multiplying all the x values by -3. So this one is 1, it's going to become -3. This is 2, it's going to become -6. And we're using those green points. This is a 4, so it's going to become -12. And I think we might not be able to fit anything else. Just trying to make sure it's on the same y value. And then this one is at 8, that's 24, so we're done. So we're going to try to connect the dots in a curvy and attractive manner again. Doing your best. And we still have a vertical asymptote at x equals 0, so I'm not going to relabel that. Y equals -2 times, oops, didn't give myself enough space. Y equals -2 log base 2 of -1/3 x. All right. And then I usually do the two translations together. So I usually do moving left or right and moving up or down together. You can certainly do those separately if you like, but most people are able to do those together, so don't feel like you need to. And you don't have to draw 2 transition graphs. You can draw 1 transition graph, but you have to be careful that it is accurate, okay? So just watching out for accuracy. I definitely like to draw more transition graphs because I want to make sure that I have a super accurate graph. Okay? So I'm moving everything over to the right by 4 and then up 1. So taking all these blue points, moving over 4. 1, 2, 3, 4. And then up 1. And doing that with all my points. 1, 2, 3, 4, up 1. 1, 2, 3, 4, and up 1. And I'm also going to move my vertical asymptote over 4. So my vertical asymptote was at 0, so now it's going to be at +4. Oops. And I just realized I moved that point up 2. I don't have anyone here with me to tell me I did it wrong. Usually you guys are good at catching my mistakes. X equals -4. So you're always, looking out to see, okay, did I make a mistake? Is there anything that I might have done incorrectly? And I'm not going to extend too much past the points that I know. Oops. Okay, that wasn't curvy and attractive, so I'm going to redo. I know most of you don't have an undo button. That's okay. It doesn't have to be perfect, like I said. Okay. And that is y equals -2 log base 2 of -1/3 x minus 4 plus 1. Done. Okay? It does take a bit of time, but if you're careful, then it's not too difficult. You just have to know what you're doing. Actually, one more thing I want to talk about when I talk about 8.2. I did want to remind you about the mapping formula as well. X over k plus d, ay plus c. Okay. You can check your points with that as well. I'm not going to do that right now, but you can certainly check them. Okay, 8.3, since I have a little space here, I'm going to do that here. 8.3 is, actually, let me just get my notes out. I just want to get the name of it correct. Evaluating logarithms. So we did this a bit in 8.1. I didn't talk about it when we reviewed 8.1, but we did have some questions like it in the book, so we did learn about evaluating logarithms. So this actually wasn't too new for people when we learned this lesson. So we have questions like example D, evaluate log base 8 of 32. So how we did this was we set this equal to m, or whatever letter you like. M is kind of arbitrary, but it's fine. And again, feel free to pause and do this on your own first. So then we're going to switch to exponential form, and that is basically the only technique that we learned here, is just switching from logarithmic to exponential form. So I'm going to write switch from logarithmic form to exponential form. And then you solve it, right? So this is 8 to the m equals 32. You might recognize that these are both powers of 2. So 8 is actually 2 to the 3. And 32 is 2 to the 5. So if I use my exponent rules, and a reminder, your exponent rules are a to the m times a to the n is equal to a to the m plus n. A to the m divided by a to the n is equal to a to the m minus n, and a to the m to the n is equal to a to the mn. These are important exponent rules that we're going to be using. And most people have these memorized already because you've learned them, I think, maybe since grade 9. I don't remember exactly at this moment when you do learn the exponent rules. So I'm going to use that last exponent rule, the power rule. 2 to the 3 to the m is 2 to the 3m equals 2 to the 5. Now I have a single same base on both sides of the equation. That means that I can equate the two exponents, okay? So you have that single same base. You can equate, or I'm going to say let the exponents be equal. That means the same thing. Equate the exponents. Let the exponents be equal. Just write it in more simple language. So 3m is equal to 5. So m is equal to 5 over 3. And that's it. Okay, that's basically all we did in 8.3. Is just switching from exponential to logarithmic, or logarithmic to exponential, and then solving. All right. It's in 8.4 that we get a little bit more complicated. 8.4, we learn the log laws, the logarithmic rules, if you want to be like that. Okay, so log base a of mn is equal to log base a of m plus log base a of n. This is based on this product rule right here. So these are related, okay? Log base a of m over n is equal to log base a of m minus log base a of n. And the bunny hop out rule, log base a of m to the n is equal to n log base a of m. And one more rule that we learned is log base, let's say log base a of b is equal to log base m of b over log base m of a. And so this is really a useful rule if we're trying to evaluate exponents. Or not exponents, sorry, logarithms. So log base 8 of 32, because my calculator and most calculators only have base 10, remember that if you see just log without a base sitting there, it's secretly base 10. So you can actually rewrite log base 8 of 32 as log base 10 of 32 over log base 10 of 8. And you can type that into your calculator and find that answer. So for that reason, you're probably not going to see a lot of questions like this evaluate on your test unless it says show all your work, in which case you would have to show all of this work in order to justify your answer, and you won't get much for just typing it into your calculator. Okay? So yeah, you can do it this way, or you can change it to whatever base you want. It could be base 2, could be base 5, whatever you want. But because our calculators do base 10, we usually go into base 10 there. Okay, so we've got our 4 log laws from 8.4. We're going to go ahead and use them. There's two types of questions that we started with in 8.4, and then we started to get a little bit more complicated after that. So we could do either simplifying this by using, so we're actually expanding it out and getting rid of all of the, like we're separating them into log base a of x, log base a of y, log base a of z. And the other type is to say, okay, let's write this as a single logarithm instead. So you're going to compress all of those into one. Okay, so I'm going to let you pause and do that. As for me, I'm going to, well, I'm sure once you've paused it, you're going to unpause it, so I'm going to start. So hopefully you've done this already by the time you're listening to this. So there are multiple ways that you can attack example E. I'm going to do it one way, and if you do it a different way, but you get the same answer, then that's a totally fine answer. Don't worry about it, okay? So if you don't do exactly the same steps as me, that's totally fine. Everyone's going to approach this question in a slightly different way. So this is log base a of the square root x to the 5 y cubed over z to the 8. So I'm going to rewrite that as x to the 5 y cubed over z to the 8 to the half, because the square root is a half. So this is, I'm going to bunny hop it out first. You don't have to bunny hop it out now. I think when we did this in class, we did not bunny hop it out. If you're listening to this years later, then you may, I mean, who knows what you did. So this is equal to half log base a of x to the 5 y cubed over z to the 8. So I bunny hopped out my half, and now I'm going to open that up. And when I do open that up, I am going to have to put a bracket around it. So log base a of x to the 5 plus log base a of y cubed, using that product rule, minus log base a of z to the 8, using that quotient rule. I'm going to bunny hop those all out, and at the same time I'm going to do distributive property. Naturally, if you do not want to use 2 steps at once, feel free to do one step, like show extra steps. Totally fine, no problem with that, okay? So 5 over 2 log base a of x plus 3 over 2 log base a of y minus 4 log base a of z, because 8 divided by 2 is 4. And now I have my log base a of x, log base a of y, log base a of z. Nothing is interfering inside of the argument, so this is done. Okay. All right, let's do example F. So we're doing this backwards. Write as a single logarithm. 5 log base 2 of x squared minus 3 log base 2 of y plus 10 log base 2 of z to the half. So I'm going to bunny hop those in, log base 2 of x to the 10. And just a reminder that you cannot do the product rule, the quotient rule, if you do not have the same base. So I can see that these are all base 2, and that is important. Log base 2 of z to the half times 10, which is 5. Okay, this 10 comes from being 2 times 5. Technically what I did is log base 2 of x squared to the 5, and then I skipped a step. Okay, so that's what's happening in there with the math if you are not sure about that step. And I'm going to put these together using my quotient and product rules. So I have a minus with the log base 2 of y cubed. So I'm going to do log base 2 of x to the 10 divided by y cubed times z to the 5. I do want to put brackets around it just because it's quite a large argument, just to make it much more clear to read. You don't always need brackets around your argument, but it just makes it easier to read, so it's better if it feels unclear at all, then do it. Okay? All right. 8.5, 8.6. 8.5 and 8.6, solving exponential equations, solving logarithmic equations. So 8.5 was solving exponential equations, 8.6 is solving logarithmic equations. Did I say logarithmic twice? 8.5 solving exponential, 8.6 solving log. So there's really just two strats here. Strat number 1. So first of all, we want to make sure we're trying to use all of the rules that we need. So you might want to try out any log laws or exponent rules. And then once you've done that, you can use one of these two strats. If you've got a log or an exponent on one side and a number on the other side, then you can just change it from logarithmic form to exponential form, or from exponential form to logarithmic form. So changing from exponential to log, or log to exponential form. Strat number 2. If you have exponents on both sides, or you have logs on both sides, and you have the same base, so same single base on both sides, then you can equate the arguments, or you can equate the exponents. So same single base. So we've actually seen this technique already. We saw both of these techniques in 8.3. Same single base. Equate arguments if it's logs, or equate the exponents. Okay? So example G, you can pause if you like. I'm going to talk about the strat. Example G, I've got exponents on both sides, so I'm going to use the log laws. I don't have the same single base yet. I have a 9 and a 27. Those are different bases, so I want to get to the same single base. So I'm going to change them, and then I'm going to use strat number 2 because I'm going to have exponents on either side. So, oops, just trying to move up here. And if you want to try example H as well, you can. Go ahead, of course. So this is going to be exponents of 3. This is 3 to the 2 and 3 to the 3. So we did a question very similar to this already. 3 to the 2x plus 2 equals 3 to the 6x minus 9. Now I have the same single base. I've got that 3 in my base, so I'm going to equate the exponents, and then I'm going to solve. So I'm going to move that 2x over here, and I'm going to move the negative 9 over here, and so x is equal to 11 over 4. Okay? So for the next one, again, we're solving exponential. Here we got to use that exponent rule of 9. So because I've got 9 to the x plus 1 minus 4 times 9 to the x, so this is a little bit more complicated than the other one. I don't have just an exponent on either side. I've got a number there as well. So I'm going to try to put it all into one exponent there. So this 9 to the x plus 1 is actually 9 times 9 to the x using the exponent rule. Oops. 4 times 9 to the x equals 405. And you can use that substitution technique that we talked about, let u equal 9 to the x. So, because I've got two 9 to the x's, and I'm going to replace them. Okay, you see that? So that makes it a little easier for people to see. If you don't want to use this technique, you don't have to. Oops, I put the wrong number there though. My brain was working a little bit ahead. Always looking back at your work, checking your work. 5u is equal to 405. Okay, so u is equal to 81. Because 405 divided by 5 is 81, I think. So now I can replace it back with 9 to the x. 9 to the x equals 81. And I know 9 squared is 81, so x is equal to 2. Okay, just like that. All right, we got 3 more. So for this one, again, we're doing exponents, and we're going to have to use exponent rules. This 3 to the 2x is telling us that we've actually got a secret quadratic going on. This is 3 times 3 to the x squared minus 7 times 3 to the x plus 2 equals 0. So watching out for those quadratics, I'm going to let 3 to the x equal v, or whatever you want. 3v's, well, I wouldn't use x, but any other thing should be okay. 3v squared minus 7v plus 2 equals 0. You can use quadratic formula. I'm just going to use, I'm just going to factor it. So now I get v equals 1/3 or v equals 2. And I can replace v with 3 to the x, or 3 to the x equals 2. Now 3 to the negative 1 is 1/3, so x is equal to negative 1 here. And 2 is not a power of 3, so I'm going to just put that into logarithmic form. X equals log base 3 of 2. If it doesn't ask you for the decimal, you can just write the exact value, so just writing it as a logarithm, and that would be totally fine. Don't need your calculator for that. All right, moving along. Now we're looking at solving logarithmic, but we're still using the same strats. We're just going to use the log laws, and then we're going to try to use either strat 1, which is change it to exponential form, or strat 2, which is equate the arguments. We've done this before. We'll do it again. So this is a plus, which means I'm using product rule. So log base 5 of x minus 1 times x minus 2. I'm just actually going to put a square bracket around that so I can see that it is one argument, equals log base 5 of 12. Now I've got a same single base, so I'm going to equate the arguments. X minus 1 times x minus 2 equals 12. You can skip a step here and expand that open at the same time if you like, but I'm just taking it a little slower. Minus 3x plus 2 is equal to 12. So I expanded that x minus 2 times x minus 1. X squared minus 3x minus 10 is equal to 0. So x minus 5 x plus 2 is equal to 0, x equals 5, or x equals negative 2. So using those quadratic skills from grade 10 that we've been using the whole course. Now, one more thing, when you're doing logarithmic, you do have to make sure that the base and the argument are not going to be negative. So make sure base / argument are positive. They also cannot be 0. Positive numbers do not include 0. In this case, x equals negative 2. If I plug that into x minus 1, I'm actually going to get, or sorry, let's go to the original, x minus 1. I'm going to get a negative number. If I plug it into x minus 2, I'm going to get a negative number. So that is an inadmissible answer. If I take the 5 and I plug it into x minus 1, I get 4. Plug it into x minus 2, I get 3. So those are both positive numbers, so that's my only solution. Okay? So, like I said, 8.5, 8.6, using one of those two strats, but it's just the tricky part is remembering your log laws and using them, remembering your exponent rules and using those. Okay? 8.7, word problems. All the word problems that you're going to see are going to give you the formula, so you don't need to worry about them. A equals p times 1 plus I to the n for compound interest. Remember, A is the amount, P is the principal, that's the initial amount, and then you have to worry about I, compounding period, so don't forget to do the per annum divided by the number of compounding periods per year. Right? Half-life formula, A equals A naught times 1/2 to the T over H, where H is the half-life, and we're doing a half because it's half-life. A naught is your initial amount. Okay? And then we did things like, in your textbook, there's things like light intensity, there was pH, there was Richter scale, all sorts of things that you will get the formula for. Okay? And then let's do this last question. So 8.8, instantaneous and average rate of change. You know that the average rate of change is the slope of the secant, which is delta y over delta x. Instantaneous rate of change, slope of the tangent, f of x plus h minus f of x over h. Okay, so this question is asking for instantaneous rate of change. So we're going to do f of x plus h. And usually we use h as 0.01, 0.001, something like that. A very small number. So I'm just replacing with 3.01. So log of 3.01 minus 1 plus 2 minus log of 3 minus 1 plus 2, using brackets, over 0.01. You can just type that into your calculator. I'm going to type it in right now. Okay, my calculator isn't working. Just use my phone. Oh, calculator slowly coming to life. No, okay. Sorry about the delay. Just even trying to find my calculator always delays us a little bit. All right, so log of 2.01 plus 2 minus log of 2 minus 2 is equal to, and divide by 0.01. So my calculator gives me 0.216606 blah blah blah. So a reminder that you do need to round that off when you're using instantaneous rate of change. In this case, there's nothing convenient like 0.21999999, but you know, it's pretty close. We're getting some silly numbers up in here, so 0.22 should be good enough. Wherever you decide to round to, just make sure you're cutting it off at some point. Okay, and so that's the review for Chapter 8. So rates of change, word problems, solving exponential equations. We use this in 8.3. We used this in 8.1. Those are the same strategies all the way through. Got your log laws and your graphing, and that's about it. So it's a pretty short unit. Hope you enjoyed this video, and I'll see you in class. Bye.